On in, everyone.
Good morning, Mr. Younger.
Good morning. How's it going, Elijah? I think that was Elijah.
It was.
Okay. The pause made me worry that I was wrong. Today's the 17th. That done. A minute and a couple more. Anybody have any questions before we get started?
Is it confirmed that today would be the last Zoom call, or are you still debating on that for next week?
Uh, I would say the best route for us to go is to assume that I'll be there next week, and I'll have to email you over the weekend if something comes up and doesn't let me do that.
Awesome. Thank you, Mr. Younger.
Yeah, I'm happy myself.
Are you feeling more recovered from the surgery this time around, or?
Yeah, the only thing is I just have this stiffness where I can't lift my arm and it aches when I touch it, so it's kind of a pain in the butt. But it's not going to keep me from doing anything, so that's the main thing, I guess. The only thing
Yeah,
is
that's
I
good.
can't right now lift my arm, which is problematic in the event of driving. So, all right, now I got this open. And it was mainly because they had to build so much bone inside of my bone that he's not allowed me to do. Normally, within like 2 weeks, you'd be doing physical therapy where you're changing your range of motion and strength and building and all that stuff. But I've only been allowed to like bend over and swing my arm like this, but only with the weight of my arm hanging down, not with any strength, because they're wanting that bone to heal. So it's made it, a little bit more problematic, which would have been, that was a lot less of a matter with the first shoulder replacement, but this one I sort of screwed up my whole shoulder blade, so it stinks. My undergraduate advisor, actually my he was actually my master's advisor and sort of one of my undergraduate advisors. But anyways, he knew I like sports and stuff like that. He said, "I tell you what," he said, "don't play sports." He said, "My wife was athletic and she was into snow skiing and played a lot of softball and all these different sports." He said, "And she's had two hip replacements. She needs a knee replacement. She's probably going to need another knee replacement. Her wrist is all shot. She's all." I just laughed at him and thought, "Yeah, that might have happened to her, but I'm sure it's nothing. It's just." But here I am, because I did a little bit more activity physically than than some people. I am constantly in pain, broken back, torn ACL, need two knee replacements, have shoulder replacement, had to replace a shoulder replacement, need another shoulder replacement, two carpal tunnel surgeries, just a couple things. All right. Well, it looks like it's really time. It's 9:01. I've got everything set up and ready to roll. This is lab. I don't know why I just saved it as it was not lab. I'm looking at my document that we're using on on my iPad. So I want to go ahead and navigate my Canvas page back to this week, and then I'm going to share screen with you guys so you know what we're doing in lab today. Another person came in. Another person came in. So this basically is it. Okay, that's cool. All right, so let me do my share screen. It looks like most people are here now. While I'm waiting for this last few to log in completely, I will make another announcement of what Elijah asked me about earlier. So I just want to remind you guys that my battle plan is that I am coming back to regular work next week. I will have to send you an email over the weekend if something comes up. The latest I could imagine doing that would be Sunday. So I definitely check your email Sunday, probably in the early afternoon, 4 or 5 in the afternoon or something like that. That'd be the latest I'd let y'all know. But if you don't hear from me by then you can assume that we're going to report at class like normal on Monday and Tuesday and Wednesday, Thursday, and Friday of next week. So everybody got that, hopefully. All right. So I did share screen and I shared it with my iPad, which was not what I meant to do because clearly I need to start drinking in the morning. I was planning on sharing a different screen. I mean, now I've got the right one. Okay. So this is a screen I plan on sharing with you. So this is week 2, everybody. Notice I have some old chapter 18 lectures to cover some of the material. For instance, a couple of you I know are in my night class, so y'all covered some of this last night. But here's some other stuff. Here's the chapter 18 homework. I probably have to go set those due dates, and I'll do that while you guys are in lab. What you'll see here is sequence 2, lab 2, electric fields. This one is the one we'd be doing if we were in a class in an actual lab setting. But because we don't have the lab setting, we're going to do this lab. So everybody pay attention. This is the lab that we're doing. Electric fields and equipotentials with PHET. Okay, that's the key thing. So what you all want to do is go ahead and click on that and download it. That's the document you're going to be using. Do not click on the other one. I mean, you can click on it and look at it. The whole reason I left it there was I wanted you to have some feel for how we could do these exact same experiments in the lab. So seeing that lab write up can be a little helpful. I'll tell you what we had. We had a sheet of carbon paper. So basically, if you look at this carbon paper, it looks sort of like regular paper, but one side is sort of a little more shiny, if you will, but really it's basically carbon infused paper, and it's got these little metal routes on it. So like it's got a little sheet of if you imagine like aluminum foil, maybe made out of brass or bronze or something like that, think about something about that thin. And bare minimum, it has a little piece of that running from one of the 8.5 edges because the papers are about 8.5 by 11. So imagine one of the 8.5 edges having perpendicular to its center a little ribbon like this that's maybe 2 inches long and then has a little circle on the end. And then the other side has the exact same thing. That would represent 2 point charges. Okay. Now the metal going, which is that little ribbon and then the little circular end and then the ribbon over here and then its little circular end, that's the metal. So that's representing basically a point of electric potential that's going to be a constant because metals are conductors and except in a non except in a non-electrostatic situation, the voltage is on a surface of a conductor is a equipotential surface. So what that means is that whole ribbon on this side has a set voltage, and in fact, if we set that voltage to, let's say, uh, if we connected it to a power supply with a DC voltage of 2 volts, then that whole surface of that ribbon would have a voltage of 2 volts. And then if we took the other one and connected it to the ground side of a DC power supply, that whole thing would read 0 volts. And because there's carbon in between the two ribbons with the balls on the end, that carbon is sort of like a conductor. So you can actually take and put, for instance, one probe of something we call a galvanometer, which basically measures very, very small currents. You can put one probe of a galvanometer on anywhere on that carbon sheet. We're choosing to stay away from the metal ribbon. And you put the black one there, and then you put the other one anywhere else, and you keep doing that until you find that the other probe, when positioned at this new spot, gives a voltage of zero, or excuse me, gives a current on the galvanometer of 0. If that's the case, then the only reason current doesn't flow is that the voltage difference is 0, and therefore you've now found two spots: the spot where your one probe was and the spot where your other probe was. Those two spots have the same electric potential. In other words, they're the same voltage, and volts is literally coulombs per, or excuse me, joules per coulomb, which we call a volt, but that's where the unit comes from. So you can sort of think of it like a potential energy thing. So this is joules per coulomb. The joule part makes you think potential energy. So you keep holding that one probe down and moving that other probe all around the carbon sheet until you find a string of spots, all of which have zero current flowing. So when you do that, that actually makes one equipotential line. I'm going to now that I've explained what this is about and how that sheet comes into play, and I'll show you the sheets in the next lab just so you'll have an idea what they look like. But just the fact that they're using carbon and they're using these little metal ribbons in it, you can make the structure anything you want. So like I said, if I did a ribbon with a big circle on the end and then another ribbon from the other side with a circle on the end, the two ribbon flat parts don't matter too much between them. The most important thing is the thing closest to the middle, and therefore that's the two circles. So that circle's acting like one of high potential, and then this circle's acting like one of low potential, and we're mapping out exactly where the lines of equal potential are. You could also take that ribbon and instead of putting a ball on the end, you could run the ribbon from the 8.5 side and then run the ribbon upward and then back downward. And then that would make like a single flat plate. And then you could do the other thing, the same thing on the other side, and you'd have two parallel plates like that. Or you could have one parallel plate and a ball on the opposite side. All of those are different configurations of charges. And by doing that, that actually allows us to almost directly measure electric field lines, which are something we're going to encounter in chapter 21 and 22. So that's what this lab's about. Let me go ahead and now that I've showed everybody, remember everybody, this is the sequence 2, lab 2, electric fields and equipotentials with PHET. That's the key. That's the one you want to download. So make sure you download that. I've set the due date properly for lab 2, and this is where that's turned in. Of course, last week you were supposed to have turned in your lab right here. So hopefully everybody's already done that. Excuse me, right here. So hopefully everybody's already done that for this week because it was due this morning at 9. I don't think I gave you an extension on that. No, I didn't. It was the 241 class. All right, so let me stop sharing that. And now I'm going to share my iPad screen again. So share screen, iPad, like this. Anybody have any questions while I'm waiting for this to load up?
Younger. Um, Yeah. Hi, it's me,
Yeah,
Shonda.
Shanda.
Hey, I sent you an email last night and about the lab for the
Right.
review last week. If I could have an extension till either tonight or tomorrow, I was really sick with had all these steroids and
Gotcha.
antihistamines for a week because of that, and that's all. And then
Well, I tell you what,
it's
I,
just
I never allow extensions on the lab,
it
strictly
was such a
speaking.
basic. Yeah, it was
You,
yeah.
you are
Go ahead.
asking for the extension on the lab, or are you asking for extension on the homework?
No, the lab, the homework's
Yeah,
almost all done. I'll get it done tonight. The lab, I went. Yeah, I just.
gotcha. Yeah, no,
Yeah.
no problem. I tell you, I don't necessarily give extensions for labs, but here's the good news. The good news is that I also don't take off late until I grade it and it's not there. So if you get it in before I grade it, then you're going to
Okay.
have no points taken off anyways, this time at least.
Okay. All right.
Okay.
That's fine. Yeah. It's just the review. It wouldn't take long. I'm trying to get it done this morning. Well, right when I got back, and then it took forever to find the passcode and your phone number for this lab. I was taking a lot of antihistamines last night. I was like, oh
Yeah.
my God. Oh,
That's right. You're in my lecture class at night, so it's only
yeah.
from the email I sent you. Gotcha. Okay, no problem. Yeah, don't worry about that. Like I said, I
I'll
probably
just
won't
get
be
it.
grading it until this weekend at best.
I'll, I'll have it done right after the class. It's the review spreadsheet. It was no experimentation. It was just making Microsoft Excel spreadsheets from the formula.
Gotcha. Yeah, no
Um,
problem.
yeah, and the other
Just
question was about the extra credit on chapter 16. They talked about that last night. I finally had to go in and for some reason, every time I tried to go through the Canvas, it
mhm.
just gave me an error. I had to reload it through the My Pearson for me to get into the
S-
homeworks again.
Sometimes that happens. Sometimes you just need to empty the cache. I had a lot of people complaining this weekend about not being able to get in. They kept getting
It
error
just gave
messages.
me
I
an
could tell
error
them to,
message every
yeah,
time for the
just empty your
16.
cache
So
when that happens. If it doesn't work after that, then immediately contact Pearson support. I can't help with any of that,
yeah, because
but
it said the 16 wanted to be in last night, so I don't know the extra
yeah.
credit. It was due yesterday on the 16th. I don't know.
Yeah, so yeah, and that's that was the due date I settled with just because I'd given you extra days on that. But yeah, just in the future, whenever that happens, like I said, always the go-to thing is try logging out,
Pearson.
logging back in, closing your browser. And then if that doesn't work, try emptying your cache and
Yeah,
then
I found it
again.
this
And if that
morning.
doesn't work, you go to Pearson, My Lab and Mastering for
Yeah, I
support.
had to get all the way out of Canvas and not go through there and just sign in off of the regular site and then find it that way because
Right.
it totally blocked me through Canvas.
Okay.
So now I
Uh,
have two accounts. So now they gave me two accounts for Physics 242 at Pearson.
Oh, well, we might have some problems. I have to talk to you about that to be sure. There's if you actually are accessing it through any way other than Canvas, then I'm never going to get your scores, and that
Yeah,
could
see,
be
that's
ongoing
why
problem.
that's what I'm trying to tell you. When I did the extra credit, tried to go through and do it. This was yesterday. I got a bunch of error messages and then it didn't let me through Canvas. And now I have, when I log in off of Canvas to regular my Pearson, I have two accounts that say Younger Physics 242. I don't know what they did.
Yeah.
Yeah.
So let
So I
me
have to
figure
figure out
out
which
what
one
that
you'll
is.
get.
Put something special in the username for it if you can, like change the username by adding an asterisk or something that you can change them, so that I can look and say, hey, this one's the right one. So that
Yeah,
would
they
help.
gave me two. It's not just the same one duplicate. They gave me two different account numbers. That's how I had to fix it to find 16.
Right.
I
That
don't know what they did because I
yeah.
didn't sign in or add any additional information.
Yeah, I'm not sure about that, but we'll figure something out.
Okay, I'll
All
get
right.
that done.
All right. So what I've drawn here on the screen is basically the board that we would be using if we were doing this in lab. And then what I'd lay on top of that is this carbon paper, which will be represented by black right here. So this carbon paper is basically a paper that's infused with carbon so that it is not a good conductor, but it has the ability to conduct electricity. Now, over here at the side in the actual carbon paper, they had as a bare minimum a little ribbon of metal embedded in the paper. So that's what I'm drawing in red. And what I just suggested was, for instance, the piece that had a circle on the end. So that is one particular setup. And what you're supposed to be seeing here is that basically this blue little tab that's got two little circular things on it, this part right here, that is a piece of metal. This screw over here and the screw to the right, both of the two little circles on that piece of metal are metal, of course, as well. And this is also a metal tab with screws on it as well. So what you would do in principle is you take your multimeter, or excuse me, your power supply, not your multimeter. You take your power supply and you look at the DC side, and you'd have a red terminal and a black terminal like this. The red represents positive. And what you do now is take a wire from the red terminal and run it up here and connect it to that. And then you take a wire from the black terminal and run up here and run it to that. So now what we have, if let's say this is 2 volts. So let's say that's 2 volts. Then what that means is this part right here is at 2.00 volts. and this part right here is at 0.00 volts. Okay. Now, the nature of Coulomb's law, which is really what we're studying here, Coulomb's law is the law that tells us how the electric field or how the force is related to the charges. So in terms of electric field, you could say electric field is equal to some constant times the charge that's causing it divided by the square of the distance between them. Okay, because that R is in the bottom and the E is in the top and they're on opposite sides of equals, that means they're thumbs up, thumbs down. So the larger R is, which is the distance from the charge to the point in space, the larger R is, the smaller the electric field is. That's why I was telling you that, in fact, between the probes right here, the little bits of metallic strips, between them, those circles are all that really matters. This whole surface, however, this whole red thing would all be an equipotential line because it's a metal. Okay. So that's equipotential surface. Now, what we're trying to draw here is the equipotential line so that we can use it to map out the electric field, because it turns out the equipotential lines are always perpendicular to the electric field lines. So what we're going to do then is we're going to also take a galvanometer, and this is what a galvanometer looks like. It's normally like this, and then like this. Something like that. And in fact, it normally has a dial like this, and it has a rod, basically like a needle, that points straight up, and this corresponds to 0 amps. This corresponds to amps greater than 0 in a specific direction. And this corresponds to amps greater than 0 in opposite direction. Okay, so that's the way that thing works. It basically has a way to connect wire to it, and then another one as well. One of these is obviously the positive, one of these is obviously the negative. So if, for instance, current comes in the red and comes out the black, then the needle will deflect to the right, which is what we normally call the positive direction. And if it comes in the black, we'd see that over here. Okay, so that's what that means. So what we're going to do is we would normally take and connect a wire to it, and then we come down and touch the wire right there. That's just one spot. Now what we're going to do is take the red wire and connect it to various spots. Like that. Like that. And what you ultimately, ideally, will come up with is a series of lines along which it has an equipotential. So all of these read 0. points, red 0 for black probe at A. So I'm going to say this point right here is A. Now what we could then do is put another black probe at, say, B. And then what we get is I'm going to try to use a different color just to keep it from getting kind of hard to follow. I'm going to say then what we found is all of these points read 0 volts. Or read 0 amps, actually. Okay. And we can keep on doing that sort of thing. And this point may be, for instance, C, in which case like that. And then another color, which might be right here. I'm going to say this is D. Ooh, this is D. Sorry about that. Okay. And now this guy, whoa. This guy goes straight across just like this. And then we try another color. Let's say this is E. And what we get is something like that. And then F. This one would do something like this. And let's say the next color I did was pink. So I'm going to say this is G. And this one will lay like that. Okay. So that is physically what we'd be doing in the lab setting. Okay. And by doing that, what we found is the lines of equipotential. So let me go back next page and draw that sheet out without doing 3 dimensions and stuff like that. I'm just going to draw it in straight 2 dimensions. So what I'd say is the sheet looks roughly like this. Okay. And what we had was, in fact, a little probe that came out this way, and then a circle that way, and a little probe that came out this way, and a circle that way. These are supposed to be roughly the same size. Let me see if I can shrink that a little bit, make it a little more reasonable. Yeah, that's good. Okay. What we ended up finding out was that we had equipotential lines that went like this. And then there was another one like that. Now, that's what the equipotential lines came out to be. And notice that's supposed to be what those lines are showing. Do y'all see how that's related? Anybody have any questions on how they look the same? Okay, so this side corresponded to the 2.0 volts. So I'll put 2.00 volts, and this one corresponds to 0.00 volts. And in principle, what that tells you is probably this first blue line on the right might have a voltage of, say, V equals 0.50 volts, something like that. And this one might be 0.75 volts, and this one might be 0.85 volts, and then this one would be 1.00 volts, 1.85 volts, maybe 1.75 volts, and oh, actually, it's supposed to be getting higher. Sorry about that. So let me fix that a little bit. So this one should have been just 0.15 over. So that'd be, whoa, Nelly. That'd be 1.15 volts. This would be 1.25 volts. And this would maybe be 1.50 volts, something like that. Now, in principle, what we could do to see that is we could actually, instead of measuring the fact that all the dots along, say, the V equals 0 volt, 0.50 line, instead of measuring that with a galvanometer, what you'd want to do is stick a voltmeter on part of it and then measure it relative to the zero. So you can put the red probe on the blue line and the black probe from a voltmeter on the red circle to the right. And that would read the 0.5 volts. That's the main thing that we're getting out of here. The main thing is that whole blue line that's marked 0.50 volts is all at 0.50 volts. And the electric field, E, is technically defined to be the negative gradient of the voltage. Now that's some calculus, that's some actually something from vector calculus called the gradient. And what it is this del, this triangle, upside down triangle, is called the gradient. And it's thought of as a vector operator in that, in this case, if you take the Cartesian coordinates, it'd be the derivative with respect to x multiplied by I hat of whatever comes to the right. Also, whatever comes to the right will be multiplied by j hat, and then the derivative of it with respect to y would be taken, and then k hat would be multiplied by the derivative with respect to z. Now, you might notice that I'm writing not the regular d's that you're used to from derivatives. These look like backwards sixes. Those are called partial derivatives, and they're really no more complicated than regular derivatives. Well, I shouldn't say no more, but very, very slightly more difficult. So, for instance, normally you take the derivative of 2x squared with respect to x, and you get 4x, right? If you had a function that had more than one variable, let's say you had x or y times x squared, okay, you just treat that y like it's a constant. So if I had, for instance, f of x, y, z is equal to y x squared plus z squared y plus y squared z, like that, then the partial of f with respect to x is, it treats all the variables other than x as if they're constants. So that's going to be the derivative of y x squared with respect to x would be 2yx. The z squared y, that's all a constant, and the derivative of a constant is 0. And the derivative of y squared z with respect to x is also a constant because there's no x in there. Okay. Similarly, the partial of f with respect to y would be x squared, because that's just like a number times y. Yeah, Mark, go ahead.
Sorry to interrupt. The first thing in blue, is that the vector, the E vector equals negative gradient V? Is it a V?
Yes, v is in
Okay.
voltage.
Okay.
Okay. Now the derivative with respect to y of the second term, you'll notice, is just, oops, I changed colors on you. is just z squared. And then the second term or the third term with respect to y is just 2y times z. Again, treating the z just like it were the number 3. And then finally, the partial of f with respect to z would be 0 plus 2yz plus y squared. So that's really the only difference. The good news is you don't really have to do any of that kind of calculating yet. Later on in the semester, once we get to electricity and magnetism, there may be a time. But the main thing is that is the relationship between voltage, V, and electric field, E. Notice the E is a vector quantity, and notice that the I hat, J hat, and K hat appear in the formula for the gradient. So when you actually say the gradient of F, which I will write now in red. So the gradient of F is actually equal to whoa, Nelly, is actually equal to 2yx I hat plus x squared plus z squared plus 2yz j hat plus 2yz plus y squared k hat, and that lets you see that the gradient is in fact a vector. So that's all that is. Now, you can think of the gradient as sort of the quickest path. So if you think of the voltage like on a topo map, so I'll say voltage is like elevation on a topo map. Does anybody not know what a topo map is? It's okay if you don't, just ask me. But I think everybody's been exposed to that. Anybody not know what a topo map is, or anybody need help with that?
Maybe I'm just missing what the name points to. I just maybe need a refresher.
Gotcha. So let's if you imagine a map like this of an area, what
Oh,
you
you need like a topographic map.
yeah, topographic map. So yeah, you might have a line like that, and what that line means is that every point on that line has the exact same elevation, and every point on this one has a slightly higher or slightly lower depending on what you're reading elevation, and then outside of here would be lower still, and then outside of here might be like this, and then you might have another one like this and like this and like that. So you could imagine that this would actually represent two mountains next to each other, and this would be their valley in between, for instance. Okay, so that's a topo map. So you think of the voltage as if that's the elevation, and then you think of the gradient as what's the fastest way down. So the fastest way down is always going to be perpendicular to horizontal. So gradient is the direction or is in, let me make sure that's clear. The gradient points in the direction that is the quickest way up for positive or down for negative. Oops. And its magnitude is the slope. Okay. So what that means, given that also the red lines are equipotential surfaces, remember that. So those are equipotential surfaces. What that means is the actual electric field has to be perpendicular to that. So if we imagine a line right here, that's perpendicular to that. Actually, I wanted black on that, so let me draw back like this. And then it's got to be perpendicular to this one here, and then it's got to be perpendicular to this one here, and then it's got to be perpendicular to this one here, and then it's got to be perpendicular to this one here, and then it's got to be perpendicular to this one here, and then it's got to be perpendicular to this one here, and then it's got to be perpendicular to this one here, and then of course it also has to be perpendicular to this one here. So ultimately what we get is one electric field line goes that way. Notice it goes from the high voltage to the low voltage. If you do that again, you'll see that another one goes straight across here. And you'll see another one goes straight across here. And another one goes straight across here. And another one goes straight across here, and so on and so forth. So these are your electric field lines. And in fact, if you wanted to, you could say, what is the electric field between this point and this point, say? Let's say, I'm going to use a different color so I can point out those points. Let's say this is point A and this is point B. So E between A and B, that's going to equal the negative gradient of V. So what I'm going to do is I'm going to take point B, which is 0.50 volts, minus point A, which is 0.75 volts, and I'm going to divide it by the physical distance, which you can measure on this PHET program. That's going to, let's call this delta S. So that delta S is that distance. Let's say that distance is 1.20 centimeters. Okay. And now it also has to be a negative, so I'll put that negative in front of it. And what I get is negative 0.5 minus 0.75 is negative 0.25 times the negative is positive 0.25, and then positive 0.25 divided by 1.2. That gives me 0.208 volts per centimeter, which is actually another measure of the electric field. We normally measure it in volts per meter, in which case if you multiplied 100 centimeters over 1 meter, you get 20.8 volts per meter. Okay. And really what you're supposed to do is you find that it points in that positive direction. So in actuality, it actually points the direction from A to B. So that's the direction of E. So that's the brass tacks, if you will, of the details of how you go about using that gradient. So in principle, yes, we are drawing directly the equipotential surfaces, that's the blue lines, but then from that we can get the electric field lines. So it's almost as if we're directly measuring electric field lines. And this is like one of the few experiments in nature that you can actually do. So I feel kind of bummed out in not letting you do it because we have to do it online. But hopefully, this introduction, along with the original diagram of exactly how it would be done, and this explanation of all this stuff, hopefully that all sort of fills in for what you're missing. Okay. So I think what you can see you're going to do is you're going to make a configuration in this PHET program. You're going to make a configuration that's like two charges side by side. So in the PHET program, you're just going to put a positive charge and a negative charge some distance away, and then you're going to find all the lines of equipotential. And then you're going to use the rule that the gradient, or excuse me, that the electric field lines are perpendicular to equipotential surfaces. And that allowed me to draw that first line that's horizontal, but over the perfectly level one. You see the one with all the little squares on it? That's how I drew that. So that's what you got to do. Does that make sense? All right. So we have a way where this has all been automated. With the PHET program. So instead of using the carbonized paper and a volt power supply and a galvanometer, we're going to actually do it virtually. And I should write on here since I didn't actually say that. Let me tell you, this is a galvanometer. When we learn about Maxwell's equations, we'll learn that that's basically just a little magnet with wire wrapped around it attached to a needle and then two little magnets in the device that makes that work. But hopefully, does anybody have any, hopefully everybody understands. Does anybody have any questions on the process we would have done had we been doing the actual lab with the carbonized paper as opposed to the simulation software we're going to be using?
Just a quick question. Maybe I just missed it during the explanation, but so I understood when we're taking the red knob and putting it on different points of the sheet.
Mm-hmm.
So then no matter where we put it, it would always read 0, or where would it,
Ah,
or was that only for at B and A? Like,
you missed a little complexity in there. So for starters, those little red things that I've got marked 0 volts and 2 volts on this diagram,
right,
that's part of that ribbon of metal that's embedded in the paper, so they don't move at all.
right, okay,
But you do connect a voltage source to one side and then a 0 to the other side. But then what you do is take that black wire and I put it on A, and now leave it there the whole time, at least for this first part. And then I take the red wire and I put it on all those different dots that I'm showing with the arrows. And actually, there's a lot more. But ultimately, what I discover is the only places where that galvanometer reads 0 is on those blue dots when A is at, or when the black line is at A.
okay. I gotcha. Thank you.
So those are all reading 0 amps, which means the voltage is the same between A and all the other blue dots. Does that
Okay,
make
I
sense,
understand.
Elijah?
Yeah, that makes a
Okay.
lot more sense.
Now, if I move that black wire over to point B and then do it again, then I get the green dots. And if I move it to point C and do it again, then I get the pink dots and so on and so forth. That's a good question. I suspect a lot of people, because there's so many moving parts, a lot of people probably didn't necessarily get exactly what I was saying. Does it make more sense now, hopefully, to everyone? Anybody else have any questions? So the fundamental rule for this is this whole thing right here implies that the electric field, which is a vector quantity, is perpendicular to equipotential. Oops. Okay. So that's sort of our main rule here, is that the electric field lines are perpendicular to the equipotential lines or even the equipotential surfaces. In fact, even if you wanted to do electric field here, it would have to leave perpendicular to that little piece of metal ribbon. Does that make sense to everyone? All right. So we've got that. Now let me stop sharing this screen. Again, let me give everybody, does anybody have a question on any of that before I move on to the next part? That diagram or this diagram bothersome in any way? Okay. Does everybody know why I put E equals KQ over R squared over there? That part might not have been obvious to you guys. The reason I did that, just to make sure everybody's on the same page, is that is the formula for the magnitude of the electric field a distance r away from a charge q. So if you imagine that point that says 0.00 volts, if you imagine that to be a point charge, then when I'm closer to it, the electric field gets stronger, and when I'm further away, the electric field gets weaker. And that's why I was telling you that where I put those equipotential lines, the blue dots, the green dots, the pink dots, the red dots, so on and so forth, that's between those two circles. So the circles are the part that have the biggest effect on the circuit, excuse me, on the electric field lines, because those are the ones that are closest to those equipotential lines. So that's why I put E equals KQ over R squared. In chapter 21, we'll learn more about that. All right, so one more chance. Anybody have any questions on that?
Let me just get one more clarifier because I was thinking about it. I'm sure it's gonna be more obvious when I play with the simulator.
Uh-huh.
But so like you said, you can change that black wire to any of the A, B, C, D, E, F. So if you moved it to C, how would that have altered it again?
If
Would
I
that
move the black terminal to the dot C, then I would search all around the carbonized paper for with the red probe to find all the places that read 0 on the galvanometer. And what I'd find
okay?
is only those pink dots near C are going to make that.
Okay, okay. Yeah, now I understand it. Thank you, Mr. Younger.
No problem. All right, so we got that. Let's kill this share screen, and I'm going to go to the other share screen. I know I'm deadly handsome and y'all want to stare at me, but I've got to do the physics.
Mr. Younger.
Yes.
Someone in chat, Elizabeth asked,
Oh,
what
thank
is
you.
K? Is it a constant?
That's a very good question, Elizabeth. That's an experimentally determined constant. And we get to chapter when we get to chapter 21, we'll learn, but it's basically 9 billion. That's the number. It's 8.99 times 10 to the ninth. And then it has some weird units, but it's an experimentally determined constant. And we're not even, I don't like using the K. I normally use something called 1 over 4 pi epsilon naught. So when we get to chapter 21, we'll need it. You will not need that at all during this lab. I just wanted you to understand the functional relationship between the strength of the electric field and the distance away from the charge causing it. Good question. All right, so what I'm going to do is I'm going to open up this PHET document that you guys all downloaded. And you'll see right here is a link that should actually allow you to go straight to the website, which is, I'm going to click now. Okay. And notice all this thing right here, not only it's better than what we were using because it reads the actual voltage as opposed to the difference in voltage. So what you're doing here is you're imagining that instead of like what I did on the drawing, I took one probe from this meter, the black one, and I stuck it someplace on the paper, and then I poked the red one all over the place to find all the places where it read 0. Since this one's reading voltage, I'm not doing that. What I'm really doing is I sort of took the black probe and stuck it directly on the rightmost circle that read 0.00 volts. And then everywhere I put the red probe is what this reads. So let me show you what I mean. I just left clicked on that. And now I'm going to put a point charge right there. I do like the grid, so I'm going to put that there. And in fact, in doing so, I'm going to try to center this up so I can actually use real measurements here. And now I'm going to take an opposite one and put it right there. Okay. Right now it's showing the electric field lines. I don't want y'all using that at least not for the first trial. What I want you doing is trying to find all the points that have a set voltage. So we can pick up this voltmeter here, and you see that it's reading negative 1,683. Now, if I go over here, I can see that it reads negative 5.636. Now I try to look for another negative 5.636. So I'm getting closer, getting closer, getting closer. And you probably want to do it to maybe 1 decimal place, not 3 decimal places. That's obviously going to be a little bit more difficult, but somewhere between here. I don't want it that way. Let's do it that way. So I'm looking for 636. That's 6.4. That's pretty close. So this point and this point have the same voltage. And you could click on here and say values. That actually gives you the meter and stuff like that. Or you could click on here and say voltage, and then that gives you a plot of the voltage and how it decreases over time. So your lab will tell you how to do all this stuff, but you can see that I basically have everything I need. I could just do this right here, and let's call that 5.68. Just 2 decimal places will be enough. And now I'm going to look for all the points that have 5.68. Check this out. I just hit that pencil, and that looks like it's still 5.68 again. Everywhere on this green line makes 5.68 roughly. It's a little harder to tell because you got to zoom in and stuff like that. But that's basically what that did. So I can erase that. And let's say go dead center between the two, which they're 1, 2, 3, 4, 5 away. So I need to go in the center of the third one. And that has a voltage of negative 0.92. Notice that line's almost perfectly straight. Now I'm going to come over here and move just a mere, what, let's say 4 squares away. And again, it's right along the line that connects the 2 dots, or point charges. So I see that's like that. Now let's go over here and do 4 spaces away from this one. And now let's do 2 spaces over from the thick line, which would be right about here. And let's do 2 spaces over from the thick line, which would be right about here. And now let's do right on this thick line. And let's do right on this thick line over here. And I'm doing something because I know the symmetry of what the electric field is supposed to look like. So I'm choosing very symmetric spots. If I try 1 dot away, or let's do just barely 1 dot away, I get that. And then I could do this one over here and just again barely 1 dot away. And what you see is that's more or less the lines that we found as equipotential lines when I was drawing it. Do y'all see how those look like the lines from A, B, C, D, E, and F? Now remember, once you've got that, and this is the way you can draw it, just by clicking on that, it'll actually make your equipotential lines, but you can also use graph paper, which would be ideal, or you can use graph paper built within Word, or, the drawing aspect of Word. And when you show the actual grid, you can actually go over, 4 squares like I did here to the left and 4 squares like I did here to the right. And you can say what that voltage is and then put a dot, and then you can find another spot and put a dot, figure out where that is. You can do all that, but this ultimately allows you to get all of this. Now, if I click on the electric field,
I have a question.
yes, go ahead.
So you want us to print off graph paper and draw this, not screenshot it?
Yes, you can use the screenshots, which I highly recommend. Anything it tells you to print, definitely just do a screenshot and include. But it'll tell you the instructions exactly what it wants you to do far as the graphing. I was just making a hypothetical that you could map it all
Uh,
out, because literally what we do,
Okay,
yeah, what we do in
I
the
just didn't know if you wanted a hand graph.
yeah, it'll tell you. I think there might be one where it's asking for that, and then the rest you don't do. But if we were doing this in the classroom, what you were given would be a graph paper with the actual ribbon. Remember the brass or bronze ribbon that's in the carbonized paper? It's got the shape actually drawn on it, and the carbonized paper has coordinates 1, 2, 3, 4, 5, 6, 7, 8, 9 up to 22, and then vertical lines, and then it has other coordinates 1, 2, 3, 4, 5, 6 and horizontal lines. And you could go in and basically figure out what the X and Y coordinates of each point is as you're determining the points that have zero. In that case, it was 0 amps between point A and wherever you put the red probe. So you'd make all those dots on the graph paper, and then before you move the black one to a different spot other than A, you connect all those lines so you know they all go together. Connect all those dots so you know they all go together. And it's not really connecting the dots, it's try to find the line of best fit again that's smooth. And then you do point B, again, get a string of dots, draw a line. But then once the lines are drawn, like the red, green lines we see here, then notice we just draw arrows leaving the potential point, the voltage center, which in this case is just a point charge. Notice this one's perpendicular here. This one's perpendicular to this spot. This one's perpendicular to this spot. This is perpendicular here, perpendicular to that one, perpendicular to that one. So you can see the individual electric field lines go like this, just like what I drew. Okay. So I'll clear all that. I'll clear all that. Now, you might also want, for instance, to make a line of charge as opposed to a single point charge. Well, if you want to do that, then you just keep grabbing these guys. And just line them up vertically like that, and do the same thing with the red one if you want to make 2 planes. If you didn't want to make planes, though, you could make 1 plane and 1 charge. So that's another shape that we often investigate. Like what we have right here is a plane and then a point charge. I think I want to move that up just a little bit more there. This one's a little off. So you can get a little OCD about this, and actually the OCD will help you, generally speaking, other than the fact that it's going to slow you down. Now we can consider, instead of that, we might even consider putting the 2 charges a lot closer to each other. Now you could do something like this. Let's mark a point. Okay. Let's mark another. Mark another. And now you can get the electric field lines from that, which obviously will be perpendicular to the surface of the circle. Perpendicular, you pretend this is just like a straight line, and then everything would be perpendicular to it. But ultimately, it does look something like that. Okay. If you wanted, instead, if you wanted 2 planes, then you do this. Just start stacking these by each other and so on. Now they're a little close together now that I've got them this way, but you can move them a little further apart when you go to set them up, and that'll be fine. But this makes basically what we call a parallel plate capacitor. And that's one of the things we're going to study. And we're going to learn that at least avoiding the edges of the parallel plate capacitor, which would be around here and around here, the electric field inside of a parallel plate capacitor is basically a uniform. It's constant. Okay. So what can we do to show that? Well, let's do this. Put a line. Put a line. Put a line. Now, if we put this even closer together, it'd be more obvious, but you're starting to see right now exactly what happens. So you can see here that the electric field lines right here should be perfectly horizontal. This one looks really close to perfectly horizontal. It's starting to get a little less horizontal, a little less horizontal, a little less. So this is actually going to bulge out a little bit and come there. But at least in this middle part, all of those field lines are basically perfectly horizontal. And the equipotential, if you actually calculated the gradient from here to here and then calculated it from here to here, you'd find that the gradient is about the same for both of those. That shows you that the electric field is essentially constant. So that's what we're trying to do. This, by the way, does allow you to actually measure. So if you wanted to do that gradient, for instance, you could say, I'm going to take the central axis here and I'm going to pull this guy right to there. I see that distance is 10.4 centimeters. So if I measured the voltage on either, let's call that 9.9. So if I did the voltage on those two, I'd say that 68.43, which is the final voltage, minus, now I'm going to do the voltage over here, 115.3. That gives me negative 46.87. I'm going to multiply that by a negative, remember, because it's a negative gradient, but I'm also going to divide it by 9.9 centimeters. That gives me 4.73, and now I'm going to multiply it by 100 to convert centimeters to meters, and I get 473 volts is the gradient from here to here. And therefore, that's the magnitude of the gradient, and that is the actual direction. The electric field points from right to the left, and is 473. Now, if I go over here and do the same thing, let's try this voltage, which is 70.66. So negative 70.66 minus, now, actually, that's not the one I wanted. Sorry about that. I want to do the one to the right of that. I'm going to move this right here. Okay, that's negative 112.7 minus, now I'm going to take the voltage here, which is negative 68.67. That gives me negative 44.03, which again, I'm going to multiply by a negative. Now I need to divide it by that distance, which I suspect is going to be very close to 9.9. A little bit smaller than 9.9. So maybe 9.3. So it was negative, it was 9.3, and now I'd multiply that by 100, and guess what? I get 473 volts per meter again. So what I found is that the electric field between these two and the electric field between these two are exactly equal, even to the nearest whole number. So just with the approximations I made, that all worked. So that gives you an idea about how to calculate electric fields. Of course, I've shown you how to calculate gradients so that you can find the actual magnitude. There's not a lot of that in this lab because it's still more or less geared towards doing the part that we did inside. But you now know all the necessities that you have and all the techniques you can want to use, for instance, to figure out this stuff. I don't remember what the sensor did, but the sensor points the direction of the electric field. So notice how that direction is always perpendicular to the field line, I mean, to the equipotential line. And notice also that it always points from positive to negative. That's the definition of the electric field, is it points in the direction a positive charge would want to be moved. So that's what that is. Any questions on that? All right, so you guys can go ahead and do that now. I'm going to stop sharing. And what I'm going to do is make up a series of breakout rooms. How many people we got in here? It looks like we got 17 in here. It's been a while since I've done this in lab breakout rooms. Okay, so I'm going to automatically assign your breakout rooms. And actually, that didn't work out like I wanted to do. Hold on a second. I'm going to say breakout rooms. Okay, I don't know what just happened, but the breakout room thing was not working like I wanted it to. It's weird. It didn't give me a. It didn't give me the normal questions and answers. Normally, it asks me how many people do I want in the room and that sort of thing. Right now, I've got 4. That's a little more than 4, so I'm going to add a 5th room. And let's see what I can do now. Oh, okay, breakout rooms. I want 5 rooms. Okay.
I got a question. I'm reading
Yes.
the
Go ahead.
Okay, I gotta join. When
You just froze up there. Might have lost you, Shanda. Oh, I think she went to her room by mistake. Come back here, Shanda.
Are they good to join though if we don't have any questions?
You can. If you don't have any questions, go ahead, and I'll be here. I'm going to stop recording in a few, but I'll be here in case you have any questions.
Sounds good.
Hey, Mr. Younger.
Yes.
So since I'm in a different Canvas course, I don't have any way to access the lab document. So would you be able to email it to me?
Yeah, I thought I even said that. Who's this talking? Was that Logan again?
Sorry.
Okay, sorry about that, Logan. Yeah, I should have sent that to you already. I'll send it to you real quick.
Oh yeah, Professor Younger, I need it too. I'll send you my email.
Okay, that would help. Yeah, thank you.
why am I not okay? So are we do not turning in the graphs? It's just, or do you want the screenshots of those? You want the screen because it says at the bottom we're just taking and doing a comparative analysis, I guess. Is that what
Yeah,
it is?
you would always err on doing more than doing
Yeah.
less. So I'm never going to
Does
take
it
off for you giving me too much stuff.
okay.
But
Yeah.
what I do is just stick to the instructions. Anything, remember the rule is you're going to fill in that document with the different color font or photos or handwritten stuff. And you're going to answer every question, do any sample calculations, and put all those things right where they requested them. That way, easily go through it. Once you have all that, you should be good to go.
Yeah, it just says don't turn them in unless requested.
Yeah, just go ahead and stick them in the document. Yeah.
Yeah. Okay.
Okay.
All right. Thanks. How do I find my room now?
There should be a thing down the bottom right.
I don't see it. Oh, I don't have my screen
in.
pulled up. I see it. I don't
You're
see
in
my
room
room
2.
anymore.
You're in room
I
2.
don't Yeah, I'm looking for how to get in there.
Can you click on the little more at the bottom right? Or can any student that's
Uh,
out here maybe tell her?
I don't see it. That's what oh, there it is, rooms. I see it.
Okay.
Right.
Where was it, by the way, Shanda? Oh, mister.
And I have another question. So, with the first lab last week, I submitted that,
Mm-hmm.
and but then I got like to another Canvas course. So now, like, where am I supposed to submit the labs for?
Okay, so
Because
you're in
there's
the
like,
other course too, so I'll have to put a link over to yours. Or actually, I tell you what, just let me think about that a little bit. Was this Logan talking again, or was this someone else this time?
yeah, that was Logan.
Yeah, let me think about it a little bit, Logan. I might just put a link on your page as well and let you turn it in that way. You can go ahead to the breakout room if you want, and I'll come in and let you know. Who was that person that needed? This person said they were going to send me an email about not being in my class, but I do see them.
Oh, hey, Professor.
Yes,
I messaged it to you. It's ML11521. Yeah.
gotcha. This is Micah?
Yeah.
Gotcha. Let me look at my.
Also, are they supposed to like send me to a new Canvas course for my lab?
Uh, you're supposed to be, yeah, you're supposed to be in the Canvas course associated with this lab, which would be DO1B, and that's going
Yeah.
to be, yeah, that's going to be an issue. Let me think about that too. Anyways, let me see.
Mhm.
ML is your, let's see, ML. Gotcha. All right, I'm going to attach this and email it to you guys real quick.
All right.
And I'll come back into your room and talk to you about that as I sort of figure out what we're going
Okay.
to do with it. All right, looks like we got everything covered here. So I'm going to stop the recording and keep the actual meeting